Our group, Edwin, Emily, Abhi, and Alan, created the music-making machine.
This is the design cycle from the engineering textbook that we used.
In the ask portion of the design cycle, we questioned what a music-making machine was, and discovered the most typical definition was a rotating cylinder that had pegs or another material that hit a resonating material such as strings or metal bars. Thus, we began to research xylophones, as they have metal bars, and music boxes because of their rotating cylinders. Music-making machines began in Asia, but eventually evolved to where you could alter the pitch of the instrument based upon increasing or decreasing the length of the resonating material, the thickness of the resonating material, or the density of the material.
Our constraint was $40 and the space of 3 feet cubed. We originally thought of a glass mason jar with water idea, where there will be a rotating cylinder with pegs that will strike the mason jars. The rotating cylinder will turn by a hand crank, similar to our final design. However, we found that mason jars are pretty expensive.
We came up with a 3-part plan to divide up the work and to divide up how we were going to build the project. The first part was the frame that held everything together, and the second part was the barrel that actually turned and caused the music. And the third part was the music itself and then tuning the bars.
For the frame of our project, we decided to make it out of scrap wood and a metal pole. To make this, we cut several sections of wood and drilled a hole together to put the whole pole through. The tools that we used to do this was a large chop saw to cut the wood into the length we needed, a power drill to screw the wood together. We used a table saw to cut the large piece of plywood that we ended up putting as a base plate, and we used a grinder to cut the metal pole to an appropriate dimension. Alright, so for the barrel, we decided to use a trash can as it's large and cylindrical, and we mounted it to the scrap wood frame that we had already created, and we used a power drill to drill the barrel into the metal pole to keep it from spinning freely, and we also used metal shears to cut some of the excess plastic off the barrel so it would spin freely.
Design for the pegs evolved over time. The initial design consisted of a cylinder that would be drilled into the barrel. We decided to go against this design, however, because we needed something that would be tapered at the tip so it could come by and flick our metal resonators, which led us to Design 2. Design 2 featured a square base that tapered at the top. We went against this design because it would be difficult to cut square holes into the cylinder. Peg Design 3 was the one that we ultimately chose, which combined the circular base of the first design with the tapered top of the second design, creating almost a Phillips screwdriver head shape.
As for the third part of our contraption, we had to make sure it played a recognizable song, in this case Jingle Bells, and that the metal bars that we had attached were tuned to the proper notes. The bars were sandwiched between 2 planks of wood, and a screw was screwed in between each one of them. The tighter the screw, the higher the pitch, and the shorter the bar, the higher the pitch as well. However, these pitches were not exact, as the math behind computing the exact length and thickness and width of the pieces would be extremely difficult. Therefore, we used a phone tuner and trial and error methods.
So one of the problems we ran into while putting the barrel section together and attaching it to the frame is that the one end of the trash can is empty. There's nothing in it. So we had to build something that would allow us to attach that part of the trash can to the metal pole. This was particularly difficult because the trash can is cylindrical. The scrap wood we had is all right angles. So to work around this, we used the natural lip of the trash can to support the flat edges of the wood and screwed the wood into the lip of the trash can, making a cross of wood on the open end where the pole could go through.
Another challenge that we faced was the 3D printing of the pegs. When 3D printing the pegs, printing them one by one would take up too much time. Each peg took about 10 to 15 minutes to print on its own. When we turned it into a 9x9 array of 81 pegs, it took 6 hours, which is considerably less than it would have taken to print them one by one. The problem printing these 9x9 sheets were that there were so many small parts that if even one of them shifted, it would cause all the other ones to go and be misaligned. To fix this issue, we applied an adhesive to the build plate of the 3D printer. That stopped the pegs from moving as much. And then a second challenge that we faced within the printing of the pegs was that the printer head would come by and knock over some of the pegs that were currently being printed. And to go around that, we created a Z-hopping script that was then uploaded to the printer, which would allow the printer head to move up and down between each print.
Another challenge that we faced was peg layout. Because the cylindrical trash can that we use is not even, I had to create a scale for each note, and that was really difficult to lay out around the whole barrel. Another challenge we face is tuning, and because we use metal and wood, temperature really affects how the pitch would sound, because heating and cooling of the surround area will affect the pitch of each note.
So on Fed Day, our one major drawback was when we put together our project, we had a problem with our tolerances. Our ability to control our tolerance was not good enough to make the tolerance as small as it needed to be for the project to work. And therefore, all the pegs did not line up with our resonators, and some would miss, and some would hit it too hard and bend the resonators, and therefore our project really didn't work the way we had intended. Another problem we had was the kind of ambitiousness of our resonators, as we wanted something that we could tune, that we created, but it turned out to be more difficult to do that than we had anticipated, and the sound quality that we got out of it was not very good. So in hindsight, we maybe should have used something that was pre-tuned.
Despite all of the drawbacks, Fed was still a fun experience for our entire group. It was interesting to see what directions that people went with their music makers, including self-playing pianos to semi-CD players. It was interesting to see how everyone got through their challenges and how they presented their machines.
To improve the quality of our music making machine, we decided to try to simplify the song, that way it's more feasible, and we also use hot glue instead of epoxy to attach the pegs. We also made a base so that the whole contraption won't move a lot when we rotate the barrel.
As a group, we decided that if we were able to do this again, that we would plan more efficiently. Instead of having a general outline of due dates, that we would have specifics that matched up with the design of our music-making device. Additionally, we would begin building earlier in the semester because when we started to build relatively later in the semester, we encountered more problems than occurred in planning. In addition to that, we would stick to the plan exactly instead of being more lenient about due dates, along with researching the materials to make sure that they were the proper constraints for the device we were constructing. Lastly, as advice to the incoming freshmen, make sure you do not put it off and brush it aside because it is a big portion of your grade and does take more time than you think. And make sure you plan ahead with that in mind, along with the fact that your exams are starting and getting heavier around the time Fed is due. Also, make sure to communicate with your group so that you can stick to this plan, and remember to choose something that you're interested in because otherwise this entire process will be very annoying and stressful.